Good day everyone, my name is Puganesa Chandran, the inventor from the College of the Engineering, along with the project leader, Professor Madhya Dr. Fidas bin Basravi. So our project title for Citrex 2021 is the closed loop water cooling system for PV module. So regardless of any solar cell technology such as monocrystalline, polycrystalline or even thin cell technology, the most common problem experienced by these solar cells is the low conversion efficiency due to the extreme rise in the solar cell temperature. This is due to the fact that as per standard test condition, the operating temperature of solar cells is in the range between 25 degrees centigrade to 45 degrees centigrade. In other words, for every 1 degree rise in the solar cell temperature, the performance of the PV module will decrease around 0.5%. So here the performance, it means in terms of the power output and also the conversion efficiency. So it can be seen from the figure 1. As the solar irradiance increases, the temperature of the PV module also increases. As a result, the efficiency of the PV module decreases, and it has the lowest conversion efficiency at the highest temperature, which is at 65 degrees centigrade, and it has the highest conversion efficiency at the lowest temperature, which is the at 25 degrees centigrade. In short, we could say that the performance of the PV module is a function of temperature. This is due to the fact that the solar cells, they are extremely sensitive to rise in the solar cell temperature. Therefore, the performance, it will decrease over time. On the other hand, the effect of dust particles is also another major problem in the PV system, especially when the power plants, they are located near to the industrial zone where the rate of dust deposition is relatively higher. So basically what it happens is that some part of the incoming solar irradiation is being blocked by these dust particles. As a result, the performance of the PV module is decreased. And also these dust particles, it can transform into layers where it traps all the heat energy instead of being released to the environment, and again the solar cell temperature, it will increase. So to encounter this problem, we have integrated water cooling system in the PV in such way the water is close on top of the PV module where it can absorb the heat energy. This is because the specific heat capacity of the water is relatively higher compared to any other common substance, and also it keeps the PV module clean and free from dust particles and also foreign particles such as bird droppings. Therefore, the PV module performance, it can be improved significantly. Okay, so this is the prototype setup of the cooling system. So basically, three different effective surface area of PV module were tested under indoor condition with the help of solar simulators. So basically, three different effective surface area were chosen because we want to understand the relationship between the different cooling surface area of PV in the rise in the water temperature. And here, the principle is that the sprinkler is being used here to force out the water from the tank onto the PV module front surface. So once the water flows over entire surface of the PV module, it is collected underneath and it is being recirculated back. So in this technique, the water consumption is reduced as the water is being recycled in closed loop system. So this is the testing condition in this research study. So the only variable parameter is the volume of the water, whereas other parameters were kept as constant variable throughout the experiment time. This is to understand the effect of volume of water on the temperature profile and the performance of the PV module. So in the case of 10 watt and 30 watt, it was tested under the irradiance of 1000, whereas for 250 watt, it was tested under the irradiance of 455 due to the insufficient of halogen lamp to produce 1000 watt per meter square, as the surface area of 250 were quite large compared to 10 and 30 watt PV module. So it should be noted that although there's a limitation, but for both uncooled and cooled model, it was tested under the same irradiance. Therefore, the result is can be still compared as both have a fair comparison. So these are the optimum flow rate chosen based on the previous study, and these are the volume of water that is being varied according to the surface area of the PV module. Okay, so these are the research outcome of the cooling system. So it was found that when we integrate water cooling to the PV system, the temperature of the water cooled PV have decreased significantly up to 50%. As a result, the performance of water cooled PV have increased more than 27% in the case of 10, 30 and 250 water cooled PV. And from the figure 3, it can be seen that the temperature of the uncooled module, it has the highest temperature, whereas the temperature of water cooled PV module, it has the lowest temperature. And in the case of 10 watt and 30 watt PV module, when it is cooled using different water volume, it was found that there were insignificant changes in the temperature profile when it is compared related to each other, that is among the water cooled PV. This is because the effective surface area of 10 watt and 30 watt PV module were quite small, so the increase in the water temperature was not significant. In such, the cooling capacity of the water is not being compromised in these cases. But in the case of 250 PV model, it can be seen that the temperature of the water have risen more than 35% from the initial water temperature when 20 liters of water is being used. Whereas when we use 80 liters of water, the temperature of the water have only increased about 12% from the initial water temperature. As a result, the PV model temperature was the lowest when it is cooled using 80 liters of water. This is because the cooling capacity of 80 liters of water were highest compared to other volume. In such, it could absorb the heat energy more efficiently compared to other volume. Okay, so from the figure 4, it can be seen that the performance of water-cooled PV is significantly higher compared to the uncooled module. And in the case of 10 watt and 30 watt PV module, when it is cooled at different water volume, it can be seen that there was insignificant changes in the performance when it is compared relative to each other, that is among the water-cooled PV. But in the case of 250 PV module, when we increase the water liters to 80 liters, the performance of the PV model have increased more than 1.52% compared to the 20 liters of water. This is because the temperature of the PV model when it is cooled using 80 liters of water is the lowest. As a result, it produces a higher power output in such where the 80 liters of water it has a higher cooling effect due to the lower temperature compared to other volume. So in short, we could say that by increasing the water volume in the water tank, we could compensate the rise in the water temperature so that the cooling effect on the PV module it will be greater. Okay, so this is the cost breakdown for the total cooling system. So the total cost is around 47 ringgit, and the highest cost here is actually the water pump. But however, it should be noted that in field condition, it is not necessary to have one water pump for every single PV module. This is because one water pump it can spray more than one module. Therefore, the cooling cost it can be reduced. Okay, so these are the estimated costs for the 250 watt PV module. So it can be seen that the electricity sold by the uncooled module is always lesser compared to the electricity sold by the water cooled PV module. This is because in the case of water cooled PV module, the total power generated is always higher. Ultimately, the electric sold is increased. And in the case of the net potential saving, it was found that it has the same value as in the uncooled module after subtracting the electrical cost consumed by the water pump. So this is due to the limitation as previously mentioned where the PV module was tested under the irradiance of 450 watt per meter square. Therefore, it produces power lesser than 250 watt in the case of uncooled and water cooled PV module. So due to this, we could say that the cooling will be more effective at the peak period. This is because at the peak period, irradiance is usually around 1000 watt per meter square. So at this period, the temperature of the PV module will be extremely higher. So when the cooling is done during this period, it can compensate the power losses. Therefore, the PV module can generate more power and it will be more cost effective. So in short, we could say that the integration of water cooling system to the PV, it will reduce the payback period of time as more electricity sold in the case of water cooled PV. But it's recommended to be integrated in large scale. This is because in large scale, the net potential saving it will be higher compared to in the small scale. Perhaps in the small scale, the net potential saving might be negative due to the energy consumption by the water pump. And these are the potential market that we can integrate the water cooling system in a large scale, such as solar farm. So these are the examples of the solar farms at Malaysia. Okay, so these are the novelties and the benefits of the cooling system. So the main highlight here is that there's no external energy or external devices such as heat exchanger is required to cool the water in the closed loop system as suggested by few researchers previously, but instead increasing the volume of the water in the water tank, we could still maintain the temperature of the water in the range between 27.5 degrees centigrade to 29.5 degrees centigrade in the case of 10 watt and 30 watt PV module. And this temperature range we could still maintain under outdoor condition if there's sufficient amount of water in the water tank to compensate the rise in the water temperature so that the cooling effect of water on the PV model is not compromised. And it is applicable to all solar pumps in Malaysia, and it is also environmental friendly as it does not emit any carbon dioxide gases to the environment. And also it is easy to fabricate and it can increase the performance in PV system significantly. In addition to that, it is cost effective as the water is being recycled in closed loop system. And finally, the sprinklers are widely available and it is a low maintenance cost. Okay, so in conclusion, we could say that by integration of water cooling system to the PV, we could increase the performance of PV significantly compared to the uncooled module. And also, by increasing the volume of the water in the water tank, we could compensate the rise in water temperature in such that the cooling effect of water on the PV model will not be compromised and the temperature of the water can be maintained. And also, the cooling will be more effective in terms of cost when it is done during the peak period of time. This is because at peak period of time, the PV will generate more power output compared to other period of time. In such, it could compensate the electrical energy consumed by the water pump. And these are the previous research studies that has been published previously. So with that, I'll end my presentation. All right, thank you.